Just waiting. Okay, so we are live now on YouTube, and I would like to welcome all of you to this edition of the Wednesday Colloquium. Those who are joining through YouTube as well as through the Zoom link here within the Institute. It's a pretty warm Wednesday afternoon, and luckily we are having a good weather here in Mumbai, and hopefully not very far away from us in Pune, from where Professor Nissim Kanekar is going to give the colloquium. Hopefully the weathers are also kind. Today, in Wednesday Colloquium, we have Professor Nissim Kanekar from National Center for Radio Astrophysics, which is NCRA as we call it. It's part of TIFR family. Before I introduce Professor Kanekar, and I just want to give you a little bit of a flavor of what the Wednesday NSF Colloquium stands for. So, started by pretty pioneering vision of Professor Homi Bhabha, who was our founding director. The NSF Wednesday Colloquium aims to bring together all the faculty and students, scholars, under the umbrella of the National Sciences faculty members. And it allows for sort of getting on a Wednesday in a lecture theater and listening to experts from around the world talk about the latest developments in physics, chemistry, and biology. This has been a pretty amazing training ground for students, but also collaborations, not just within the institute, but also outside from where the speakers come from usually. So today we have an expert, an eminent expert amongst us, and we're going to celebrate one of his papers that came out in 2020 in Nature. And this Professor Nissim Kanekar is going to talk about atomic hydrogen in galaxies during the epoch of galaxy assembly. However, before he actually starts, just give a short introduction because, of course, some of you may know him pretty well in the audience, but for those who are listening to us for the first time in YouTube. So Professor Nissim Kanekar is actually an astrophysicist, cosmologist, and a professor at NCRA. He actually has been known for his research on evolution of the electron-proton mass ratio, and also for recent developments of measurement of the atomic hydrogen in galaxies, which is really a big news coming from TIFR family. Professor Kanekar, of course, is a Mumbai native. He actually did his bachelor's from Ramnarayan Ruia College, which is part of Mumbai University. And then he moved to Savitribai Phule Pune University for his master's in physics, which he finished in 1995. Then he joined NCRA for his PhD studies and then moved to Kapetian Institute at the University of Groningen for his postdoctoral work after a short stint in NCRA again. He came back to NCRA in 2009, and he has been a professor now at NCRA since then. Went up the ranks. So with that small introduction, and just mentioning that in 2017, for his wonderful work, he has been awarded the Shanti Swarup Bhatnagar Prize and other prizes that have come along his way. Without wasting much time, Professor Kanekar, the floor is all yours, and thank you for doing this colloquium, and we are waiting for it. Enjoy it. Thank you.
Thank you, Jyotishman, and thank you very much for both the nice introduction and the invitation to give this talk. I would have loved to have been at TIFR for it, but unfortunately, that is hard these days. So I'm going to be telling you about atomic hydrogen in galaxies during the epoch of galaxy assembly, and of course, the picture in the background is the instrument that we use to carry out these measurements, the giant beta wave radio telescope. And you see a bunch of about 18 antennas. This picture is taken from the Narayangarh hill, just above the GMRT, about a kilometer from the GMRT. And you get a feeling of the landscape, which is pretty green. And there are canals around the place and a bunch of antennas in a central square. The other two pictures there are people who have contributed hugely to this work. The bulk of the work of the actual science that I'll be presenting right at the end of the talk is work done by an outstanding PhD student, Aditya Chaudhary, whose picture you see on the left. And of course, none of this would have been possible without the pioneering efforts of Govind Swarup, who was the person behind the GMRT and behind radio astronomy in India, and who sadly passed away last year. So these are two people who really are important for this talk. And I appreciate that this is a very diverse audience, and I'm going to follow Max Delbruck's advice to Hershey in 1943 for a similar audience, that a speaker should assume complete ignorance and infinite intelligence on the part of the audience. And I will apologize in advance if any of you, fail to satisfy the first assumption. I also tend to speak really fast, and I will try to go slow, as I always do in talks, but I usually forget in about timescales of 5 minutes or so. In case I do, please, just say something. And of course, feel free to ask questions during the talk. So I intend to cover about 50 years of the use of the 21 centimeter line of atomic hydrogen as a tool in cosmology and galaxy evolution. And to get to this point, I'd like to give you some background to begin with. And so I'll give you a touch of cosmology, a couple of slides on cosmology. I'll tell you a little bit about how we try to understand galaxies, what a galaxy is like, and the tools that we use to probe galaxies and galaxy evolution. And then I'll get to the 21 centimeter line and how we can use it to measure the atomic hydrogen mass of galaxies. And then I'll start in the early 1970s, where the big question was, what is the matter in the universe? Is it all baryons, or is there some extra component of matter? And that is when the first direct evidence for dark matter came in. In the 1980s, the hot question was, what is the nature of the dark matter? Is it hot dark matter, relativistic dark matter, or is it cold dark matter, non-relativistic? And that's where the giant beta wave radio telescope came in. The conception of the GMRT arose because of the need to distinguish between these two models. In the 1990s, unfortunately, sadly, much mourned, hot dark matter died a death. It was killed by the Cosmic Background Explorer, the satellite that found the first anisotropies in the cosmic microwave background. I'll tell you a little bit about that. And then there was a transition with the rise of the optical telescopes in the late 90s, early 2000s. And that led to a spectacular improvement over the last 2 decades in our understanding of star formation processes across the history of the universe. Around the mid-2010s, well, it started in 2009, we began to upgrade the giant beta wave radio telescope to form what is called the upgraded GMRT, which is completed in 2018. And because of the upgraded GMRT, we could now use a tool that I will call 21 centimeter stacking to actually probe the atomic hydrogen in these high redshift galaxies for the first time. And in 2020, we finally managed to detect atomic hydrogen for the first time in these galaxies. So I hope to take you, starting in the 70s down to 2020, in fact, until a few days ago, more accurately, in this talk. So let's start with cosmology. Suppose you were telling people, somebody who didn't know anything about the universe, one fact to describe the universe, literally one fact. The fact that you probably would want to tell them is that all the galaxies beyond our local neighborhood are moving away from us, and the universe is expanding. So this is kind of a thing which was astonishing to people 100 years ago, around the time when this was first discovered by Edwin Hubble and Milton Humason, but it's something that we take for granted today. And this expansion of the universe is encapsulated in what is called Hubble's law, that the velocity of a galaxy is proportional to its distance from us, with the proportionality constant being called the Hubble constant h0. And the velocity of a galaxy is linked to its redshift. So when an object is moving away from you, waves emitted by that object are redshifted. Sound waves, light waves, we're all familiar with whistles from trains. But the result of Hubble's law is that more distant galaxies have higher redshifts. And this makes things interesting. It's interesting because the speed of light is constant. So light takes a finite amount of time to get to you from an emitting object. And since more distant galaxies have higher redshifts, what this means is that when you observe a galaxy at a high redshift, it corresponds to observing that galaxy at a very early time in the universe. Because from a higher redshift, light will take more time to get to us than from a lower redshift. So you're probing objects early on in the universe by observing them at high redshifts. And so you can actually track the timeline of the universe by observing galaxies at high redshifts. And to give you a feeling for the conversion of redshifts and time, which is highly nonlinear, redshift of 1 corresponds to about 8 billion years ago. Redshifts of 4 correspond to about 12 billion years ago. 6 is 13 billion years ago. And the Big Bang, where the expansion began, is 13.8 billion years ago. So there's not much time between redshifts of 6 and the Big Bang. It's just 0.8 billion years. And there's a lot of time between redshifts of 0, which is today, and redshifts of 1, which is 8 billion years. So that's the thing to bear in mind. Redshifts of 1 corresponds to about 8 billion years ago. The constituents of the universe, which has been a huge subject of research in cosmology for many, many, many years now, we believe today are a quantity called dark energy, which makes up about 70% of the universe, something called dark matter, which makes up 26% of the universe, and then the things that we know and love, baryons, which make up about 4% of the universe. And terms like dark energy and dark matter essentially hide a whole lot of lack of information, swept under the carpet with these nice names. We know very little about them. We have no experimental evidence for either of these quantities in the lab. Both of these come from astronomical observations, and there's still debates, huge debates about them. And one of the big questions in physics today, I would say, is what is the dark energy? What is the nature of the dark energy? What is it? Where does it come from? And secondarily, what is the nature of the dark matter? But what we have to use to probe the universe are the 4% of the energy density of the universe contributed by the baryons. We can only observe the baryons out there. And that's what we use to probe the universe. Now, the picture that we have of the universe, of this nice expanding universe, is a very simple, isotropic, homogeneous universe at very early times, shortly after the Big Bang. And this universe evolves into a complex, inhomogeneous universe with tons and tons and tons of galaxies around us today. And that can be seen observationally from the plot on the left over here, which shows an image of the sky of the cosmic microwave background taken by the Planck satellite. This is from 2013. And this is about 380,000 years after the Big Bang. And what's been done over here is that all the foregrounds, especially from the galaxy, have been subtracted out so that you can see the cosmic microwave background radiation, which is coming to us from the epoch where the baryons and the radiation decoupled from each other. And so now the radiation just free streamed away, and we see that radiation, we see the universe as it was, or the radiation as it was in that era about 13.5 billion years ago. And the remarkable thing over here is that what has also been subtracted out is a uniform constant of about 2.727 Kelvin. The remarkable thing over here is that the peak-to-peak variations, so the red things are high peaks and the blue things are negatives. The peak-to-peak variations are about 10 to the minus 5 Kelvin. So the universe is uniform in its radiation field at the level of a part in 10 to the minus 5, 380,000 years after the Big Bang. And this translates directly into the density field being uniform at about the same level, 380,000 years after the Big Bang. On the other hand, at the right, you see this beautiful image from the Hubble Deep Field made at the Hubble Space Telescope, which contains a bunch of galaxies, spiral galaxies, dwarf galaxies. There's even a star in the middle of the field from our own galaxy. And so the question in cosmology is, how did the universe get from the image in the left panel, this nice uniform universe with, with density inhomogeneities at the level of 1 part in 10 to the 5, to this crazy mixed up universe where things have dramatically overdense structures like galaxies and dramatically underdense structures like voids, a highly inhomogeneous universe. And the picture that we have, of course, which is a fairly simple picture, is that all this happened because of a very simple process, just gravitational clustering. And so what happens is that the slightly red regions over here are slightly more overdense than the blue regions. And so as the universe expands, these slightly overdense regions have a slightly higher gravitational field in the background. As a result of which, matter around them or energy around them tends to flow towards these overdense regions. And that makes them even more overdense. And therefore, they have a slightly higher gravitational field, and that attracts more matter, and so on. Conversely, matter flows out of underdense regions, and so those regions become even more underdense. And that's how, with very slow gravitational attraction, you build up these big galaxies. And so this is shown in the simulation that you see over here, starting at a redshift of 20, when the universe was reasonably uniform, going down to 0. The pink regions are regions where galaxies are forming. and the blue regions are underdense regions. And you see matter flowing along these filamentary structures into the centers of galaxies. And if you focus on the central large object over here, that's like a very large cluster of galaxies, slightly smaller than a supercluster. It's got a size of about maybe 7 or 8 megaparsecs, so bigger than say the Virgo cluster. And it's got maybe thousands of galaxies inside it. And so big galaxies or big clusters form at the intersection of these filamentary structures. And these blue regions over here are voids, where very few galaxies form. And the way in which these galaxies form, the rate of growth, and the nature of the galaxies that form at different times in the universe depend fundamentally on the constituents of the universe. And that makes structure formation, the kind of structures that form, a basic probe of cosmology. It's about the most basic probe that you can get. You simply go and look out and count the number of galaxies above a certain mass, and that tells you something about cosmology. You can use it to rule out or rule in certain cosmologies. And that's the reason that galaxy evolution has been such an important field for cosmology. It's been one of the pillars of cosmology over the last 5 or so decades. But how do you look at, what's a galaxy like, and how do you look at galaxies? So the picture on the left is a real cartoon, which just shows the kinds of things that happen that arise in a galaxy. If you take a normal galaxy like the Milky Way, most of the structure is in the form of a disk. And the central parts of the disk, the mass is dominated by stars and molecular hydrogen. And that's the central regions of the Milky Way, where there's hugely active star formation. If you go a little bit further out, there's lots of atomic gas, atomic hydrogen called H1 from now on, and there's molecular hydrogen, H2, diffuse molecular hydrogen, and there's some stars as well. If you go even further out, the mass is dominated by atomic hydrogen. So that's labeled as the interstellar medium over here. Of course, the interstellar medium is also H1, is also H2. This region also has the interstellar medium. And then beyond the disk, there is this large region, much, much larger than a galaxy, called the circumgalactic medium, or the CGM. And that contains predominantly ionized hydrogen, H2 Roman, and a little bit trace amounts of atomic hydrogen. In addition to all of this, there are what are called metals. In astronomy, all elements heavier than helium are called metals. The solid particles called dust, but these in mass are very, very, very small, although they are important for the evolution of a galaxy. And a more realistic picture is shown on the right, which kind of traces the physical processes that happen in galaxies from a nice review by Jason Tomlinson and collaborators. And this gives you a little more of a feeling of the size of a galaxy compared to the size of the region that influences it. So the size of the galaxy is about 50 kilolight years, let's say, a typical size, 15 kiloparsecs as shown over here. And the size of the circumgalactic medium is more like 500 kiloparsecs, a few hundred kiloparsecs. The scale here is about 300 kiloparsecs. And so what happens is that the way galaxy is fed is by gas accretion from the circumgalactic medium. Gas flows from the circumgalactic medium into a galaxy, into the outskirts of a galaxy, and it rotates with the galaxy. It cools down and it forms atomic hydrogen, H1. The H1 further cools.
Listen, sorry, I'm interrupting you.
Yeah.
I know you're in a flow with all the gases, but I just wanted to would like to understand this image that you're showing, which is part of some Tomlinson's article or review, I don't know. How does one get this kind of an image? Like, how do you get this information? In the sense,
okay. Let me come to that in the next slide. I'll tell you a little bit more about how you get that information in a minute.
Sure. Okay.
Yeah. So the picture that we have, okay, so actually, let me tell you about right now, what the heck. So the way you get this information is by a combination of emission and absorption spectroscopy. So what you do is that you observe a galaxy. So for example, it's very easy to observe galaxies like the central region. You can observe the disk very easily. You can observe it in stars. You can observe it in atomic hydrogen, which we'll talk about in a minute, in molecular hydrogen. The circumgalactic medium is harder to observe. And there are two ways you can do it. Again, emission and absorption. The first way is that you can observe the circumgalactic medium is made up of much hotter gas at temperatures about 10 to the 5, 10 to the 6, 10 to the 7 even Kelvin. And what you can the way you observe it is that one, you can observe it via X-ray emission. So you can actually observe highly ionized metal species, oxygen 6, oxygen 7, neon 7, various species in the circumgalactic medium directly via their X-ray transitions. And that gives you a direct handle on the temperature of the gas. The other way you can observe it is by absorption against background quasars. So background quasars are very bright in the ultraviolet. So these are basically matter accreting onto a supermassive black hole and giving out a powerful burst of a powerful continuum radiation, towards which you can get, you can measure absorption spectra using things like the Hubble Space Telescope. And you can basically observe, again, ionized absorption lines of highly ionized species, carbon-4, oxygen-6, silicon-4, and so on, from gas in the circumgalactic medium. And that gives you a handle both on the velocities, because spectroscopy gives you velocity information. It gives you a handle on velocities. It gives you a handle on motions, obviously. It gives you a handle on temperatures, and it gives you a handle on distributions. And many of these things are not easy to do, obviously. And so this is a picture that has come up over the last 20 or so years. Earlier, the circumgalactic medium was not thought of as so important. Now it's cleared over the last 20 years from direct observations, very, very, very deep observations. You can actually see these signs of gas flowing out of galaxies and coming back into them.
Yes.
So, yeah. So
Okay. This is great. This is great. Just wanted to sort of parse it out for a novice, in the sense that you, when we do traditional imaging, you would actually observe at all sorts of angles, I guess, right? Or you just do specific angles and you look at velocity patterns, and then you can deduce this kind of an image. This is all done in some sense. What I wanted to know is, what do you mean by the, so the kiloparsec is essentially the length scales that in some sense, right? So if I were to think about as resolutions of this image, length scales, resolution, what would be the resolution of such an image?
Yeah, that's a good question. So there's different kinds of resolutions here. For example, for the galaxy itself, for nearby galaxies, very close by galaxies, you would have resolutions of tens of parsecs.
Okay.
In the atomic gas, and even better than that in say with Hubble Space Telescope imaging.
Okay.
With molecular gas, even better than tens of parsecs. Parsec scale would be not uncommon for very nearby galaxies.
Right.
100 parsecs for slightly more distant galaxies would be reasonable. And certainly with HST, you can do 100 parsecs even out to outside the local group.
Okay.
For the circumgalactic medium, things are a little more complicated, because as usual, it's a combination of sensitivity and, your resolution gets traded off with sensitivity. Right. So the absorption spectroscopy comes with almost, your resolution is the size of the background quasar, which is really small, which is AU sized, astronomical unit sized. Right. And so, but there the problem is that you don't have that many quasars around. So what you're doing is a statistical thing where you take a lot of galaxies and you look at a few quasars around each galaxy.
Okay.
And then come up with a statistical picture of what the circumgalactic medium around a typical galaxy will look like.
Sure. Okay.
To come back to the question about the angles, you don't have access to angles.
Yeah.
Because you just have one galaxy you look at, and that comes with one angle.
That's true. That's true.
But what you do is that you observe a lot of galaxies, and they give you different orientations. Cool. So for example, a face-on galaxy is much easier for seeing outflowing gas, because now that gas is coming straight towards you.
Sure.
You can see it in absorption against the galaxy.
Sure. Sure.
On the other hand, in the edge-on galaxy, you can actually see the gas in emission.
Sure.
And so you basically combine information from lots of galaxies to come up with this kind of a picture.
Perfect. So thanks for that. There's a question. Yeah, there's a question by
Isn't this some sort of a model that you have with lots of observations that you put in there?
Sure. Exactly. Yeah. So this thing is not, it's not meant to be a picture of the universe. It's meant to be our understanding of what's happening with galaxies.
Okay. So it's some sort of a model based on years and years of observation.
Exactly. Yeah. So this is a picture that we think, which tells you what we think is happening with the galaxy, which encompasses a fair amount of the physics that's happening in these galaxies. But you're absolutely right. It is a model which includes inputs from a lot of observational data.
Perfect, Nissim. Thank you. Please carry on.
Okay, so that's the picture. You have this gas informed the circumgalactic medium. It cools, forms atomic hydrogen, which cools, forms molecular hydrogen, and then the molecular hydrogen fragments under its own gravity and form stars. Stars live their happy lives, and then they go bump and they form supernovae, and the supernovae chuck metals into the interstellar medium. these metals radiate and they give rise to cooling of the gas. They also, in addition to the supernovae cause cooling, but the metals are also chucked into the circumgalactic medium in the form of outflows. The supernovae throw gas in all directions, and some of the gas escapes from the disk of the galaxy. The cooling causes more cold atomic hydrogen, which results in more molecular hydrogen, and which again gives rise to more stars and back to metals again. And the outflows are very interesting, and it's been realized now in the last 2 decades how important they are. They really recycle gas in the circumgalactic medium. So what they do is that they basically chuck gas out of the galaxy, and they often reduce star formation in the galaxy. And then in addition, they balance the gas infall from the circumgalactic medium. They can actually support gas just by pushing outwards. But in addition to this, you actually this gas can fall back on the disk of the galaxy and bring down some of the gas in the circumgalactic medium just by their own weight. And so you can actually bring in gas also. So outflows play a dual role: one, reducing star formation, and two, bringing in gas. And so that's the broad picture of what is going on. And once the gas in the circumgalactic medium is basically exhausted, or certainly once the gas in the galaxy is exhausted, star formation stops and the galaxy dies. So that's the life cycle of a galaxy. What do you have to probe it? I'm going to focus. The reason I decided to go and talk about the observations earlier, but I realized I didn't have a mention of the CGM observations here. But in terms of observing galaxies directly, the things that we want to know, the big picture issues, are the stellar mass of the galaxy. What's the mass in stars? What's the star formation rate of the galaxy? How efficiently is the galaxy forming stars? What's the star formation history? Is it just forming stars continuously? Or is it forming stars in bursts? Is it stochastic, where you're producing stars in some region of the galaxy, arbitrarily here or there or whatever? Or is it quasi-uniform, that there are regions of the galaxy which continuously form stars? What is the star formation history? And the way you observe this is via observations in the ultraviolet, the optical, the infrared, and the radio. All these observations give you independent information on the star formation rate. The stellar mass comes predominantly from the near infrared and the mid infrared. And the star formation history comes from modeling what is called the spectral energy distribution, the emission from the galaxy at all wavelengths. And that's how you get information about the stars. But the bulk of the information comes from the UV, optical, and infrared, near infrared. In the case of the gas, there's molecular hydrogen, which, if you like, is the proximate fuel for star formation. And what we want to know is, what is the molecular gas mass? And at what time scale is the molecular gas mass eaten up in the process of star formation? If it's eaten up really quickly and you don't form more molecular gas in that time, star formation will stop. And the way in which you probe molecular gas in galaxies, the main way, is by what are called carbon monoxide rotational lines, which are in the millimeter. The 1 to 0 line is at about 115 gigahertz at about 3 millimeter wavelength. And so that's the standard tool we use to probe molecular hydrogen in galaxies. The next most important thing, probably, in fact, in terms of mass, much more important than molecular hydrogen, is atomic hydrogen. And atomic hydrogen is really the primary fuel for star formation. And so that is the basis of everything that we do in galaxies. And so what we want to know about the atomic hydrogen is, what is the mass in atomic hydrogen? What is the distribution? And what is, again, the consumption timescale of atomic hydrogen? And the way we get most of these is via the 21 centimeter emission line. And that's going to be the focus of this talk. So what is the 21 centimeter line? The 21 centimeter line essentially arises because there are two states, there are two orientations of the electron spin relative to the proton spin in the neutral atomic hydrogen. And one of which is where the spins are parallel, and the other of which is where the spins are anti-parallel. And these two states have slightly different energies. And so you can have a spin flip transition where the electron spin goes from parallelism to anti-parallelism with the proton spin. And that produces a 21 centimeter, a line at a frequency of 1420.4 megahertz, which corresponds to a wavelength of 21.11 centimeters, and hence the name 21 centimeter line. And this was first identified by Hendrik van der Hulst during the dark days of World War II in 1944 in Leiden in German-occupied Holland. And then it was first discovered from astronomical objects from the center of the Milky Way by Ewan and Purcell in 51 and Orton Muller also in 51. And since then, since about 70 years ago, the 21 centimeter line has been used to probe atomic gas in galaxies for a very simple reason. the 21 centimeter emission line is so weak that it turns out its emission strength is proportional to the mass of the gas in the object which is emitting. So if you simply measure the strength of the 21 centimeter line, its luminosity or its flux density, you will get the atomic gas mass. It's directly proportional. There's no problem at all. There are minor problems, but at least with one basic assumption of optical thinness, you get the atomic gas mass. The problem is that this is a wonderful line. It's used all the time in the local universe, but it's a hyperfine transition. It's a very weak line. And this makes it very hard to detect at redshifts larger than about 0.1, 0.2 with today's telescopes. And so that makes life really difficult. The second reason this line is difficult is that for a galaxy at redshifts of, say, Z, the 21 centimeter line, whose rest frequency is 1420.4 megahertz, for a galaxy at redshifts of Z, the line is redshifted to a frequency 1420.4 divided by 1 plus Z. And that is bad news. For example, for a galaxy at redshifts of 1, the line is redshifted to 700 or so megahertz. That's really bad news because we have all kinds of nasty human-made transmissions at these low frequencies. For example, cell phone bands, say in India, are at 940 megahertz and 860, 870 megahertz. Lots of TV transmissions at these frequencies, lots of satellite transmissions at these frequencies. Wireless is at these frequencies. Basically, almost every electronic device you can think of will produce unpleasant stuff at frequencies below about 1 gigahertz. And so it's very hard to detect these faint signals. I mean, they're terrifyingly faint, and then it's tough to detect them in this background of human-made stuff. So that's the bad news, and that's why it's so challenging. But the beautiful thing also of 21 centimeter is that it's something which comes from the physics of galaxies, that the H1, the atomic gas, is much more spatially extended than the stars in pretty much every galaxy. And this is shown in this beautiful picture of this wonderful face-on spiral galaxy, NGC 6946, where the left panel over here shows you the stars of this galaxy. You can see the spiral arms going out. And the right panel shows a Westerbork synthesis radio telescope image of the same galaxy on the same scale, but now in the 21 centimeter line. And you can see that the H1 goes out almost a factor of 3 further than the stars. And that, so you're tracing a much bigger region in the atomic gas than the region that's traced by the stars. And this means that with the 21 centimeter, you can probe large scales around the galaxy. And these are actual observational data from Renze Boomsma's PhD thesis. Why does this matter? This started to matter in the early 1970s. And it mattered because 21 centimeter, like all spectral lines, gives you velocity information. And so, for example, the right panel over here shows a velocity field of the spiral galaxy, the disk galaxy M33, Messier 33, close to Andromeda. The 21 centimeter line is a line. And so if gas is moving towards you, the 21 centimeter line from that gas will be blue shifted. If gas is moving away from you, the signal will be red shifted. So that means that if you have a disk galaxy which is rotating, the stuff on the top right is moving away from you. The stuff on the bottom left is moving towards you. So you can actually measure the rotation of a galaxy by simply mapping the emission in 21 centimeter. And so for this, you need an interferometer, for example, radio interferometer. But the beauty is that you can actually measure the velocity as a function of distance from the center of the galaxy. So you can directly measure how the rotation speed of a galaxy changes with radius. And this gives you what is called the rotation curve of a galaxy, which is shown in the bottom panel over here for M33. Now, for circular orbits, Newton's laws tell you that your velocity at some orbit of radius r should be given by basically gm by r raised to half, where m is the mass within that orbit, and r is the size of that orbit, the radius of that orbit. And we know for galaxies that the bulk of the mass, the visible mass, and the visible mass is dominated by stars, it's mostly in the central regions of the galaxy. And so if you say that, okay, I go to some distance beyond the central region, then all the mass, most of the mass is in the center. So you can assume that m is constant. And what this means is that my velocity should be proportional to 1 upon r raised to half at large r. And that's what you see over here. That's the expected signal that you would infer from this argument. It'll go like 1 upon r raised to half. And that's because the bulk of the matter is expected to be over here. But in the early 70s, Vera Rubin and Kent Ford found from H alpha observations that actually, things look very different. For this galaxy, things tend to keep rising. But the H alpha emission comes from near the stars. And therefore, they couldn't go very far out with H alpha. They could only go about as far as you could see the most distant stars. But with 21 centimeter, Albert Bosma managed to go much further, as you can see, about 3 times as far, in this case, yeah, about 3 times as far. And you can see for this galaxy M33, this is from a review by Salucci, that the rotation curve actually keeps rising. It's approximately flat or keeps rising. And this was first found in the 70s. And it became very clear that rotation curves in galaxies indicated that the mass in these galaxies was not enough to explain the rotation curve. There had to be much more mass well beyond the optical disk. And so in a very prescient review article, Sandy Faber and Jim Gallagher in 1979 summarized all the data and stated that it's our opinion that the case for invisible matter in the universe is very strong and getting stronger. By this time, there were about tens of galaxies which showed these flat or rising rotation curves. And that picture has remained the same even today. So what is this dark matter, this invisible matter? It is also clear this dark matter could not be baryonic. I won't tell you why for now, but take that on faith or ask about it at the end if you like. But this dark matter could not be baryonic. So there were 2 possibilities, hot or cold. Relativistic dark matter, called hot dark matter, where the particle, which is the dark matter particle, is relativistic, or non-relativistic, what is called cold dark matter, where the dark matter particle is non-relativistic. And in the early 1980s, it seemed like hot dark matter was a favored theory. And the simple reason for that was that there was a candidate hot dark matter particle, massive neutrino. People hypothesized, Eldovich and company hypothesized, that if the neutrino has a small amount of mass, that's it, you're done. There's tons of neutrinos around the place, and that's your dark matter. In addition, in the early 80s, it looked as though hot dark matter models matched observations better than cold dark matter models. And so that was very nice indeed. And an immediate prediction of the hot dark matter hypothesis was that you should form supermassive galaxies at the highest redshifts. The first galaxies that would form would be huge galaxies. They would be like proto-galaxies, but they would be thousands of times bigger than the galaxies that you see today. And this was first argued by Zeldovich and his group. Sunyaev wrote the first paper on this in the mid-70s. If you have these supermassive galaxies, they would have tons of atomic hydrogen, and they would produce a strong 21 centimeter signal. On the other hand, in the cold dark matter scenario, you would produce much smaller galaxies at high redshifts, and the small galaxies have much less atomic hydrogen, and they would produce a weak 21 centimeter signal. And the redshifted 21 centimeter line frequency was going to be 1420.4 divided by 1 plus z for redshifts of 3. That gives you a frequency of 327 megahertz. So to test this hypothesis, to test this prediction of the hot dark matter model, you needed a high sensitivity radio telescope operating at 327 megahertz. And there was no such thing at that point. And so that was the reason that Govind Swarup and his group proposed in 1984 a major new instrument, the GMRT. And it was approved about a year later and started building it in about 86, 87. And then time started changing. So while Govind and his group were building the GMRT, they also started observations of galaxies at high redshifts with the UTI radio telescope, which is their pet from the late 60s up until I would say the 90s, until the GMRT came along. And Govind and PhD student Ravi Subramanian did a bunch of observations, and they saw nothing at all. And that was a bit depressing, but UTI was not that powerful a telescope. And then 3 radio astronomers at the Very Large Array in New Mexico claimed a very strong detection of 21 centimeter emission at redshifts of 3.4 with the Very Large Array, which is the sister of the GMRT in New Mexico. And the signal that they claimed is shown over here, where they're plotting flux density versus channel number. The channel number is the same as frequency. And you can see this bump over here, about 10 millijansky bright. And if this was real, the mass in this galaxy is about 30,000 times larger than the Milky Way. So this is a humongous amount of mass, and this would have been definitive evidence for the hot dark matter model. Jodie Foster heard about this. She charged down to the VLA to observe. And shortly after that, Kandu Subramanian and Govind published an article, again, a fairly prescient article, arguing that this might not be a single galaxy, a single proto-galaxy. It might be a statistical detection of the 21 centimeter signal from a collection of small galaxies within the field of view of the telescope, within the beam of the telescope. And that was an interesting idea. It didn't get much attention. And sadly, Frank Drake and Kerr de Brown tried to confirm the signal, and it was not confirmed by other observations. And it turned out to be a fake signal from the VLA waveguides that was discovered in about 99. So that result went away, and that was that. People moved on. And then hot dark matter died. Hot dark matter died for two reasons. The first reason was structure formation. It turned out that the early N-body simulations around the mid-80s showed that cold dark matter seemed to be better matched to the observational data than hot dark matter. And that came up in 85, 86 or so, but you won't take that very seriously. The thing that really killed hot dark matter was the Cosmic Background Explorer, the satellite shown in the left panel over here, which for the first time measured cosmic microwave background anisotropies. Until then, we just had this picture of a uniform microwave background. COBE actually measured the anisotropies, and the anisotropies turned out to be too low to explain the observed galaxies at redshifts of 3 in the hot dark matter models. With that level of anisotropy, you would produce galaxies in hot dark matter only by redshifts of 1. You could not produce them at redshifts of 3. So that just killed hot dark matter. There was no way out of it. And so by the late 1990s, the standard cosmology, at that point, lambda, the cosmological constant, or aka dark energy, had come in. And so by the late 1990s, the standard cosmology was lambda cold dark matter. And sadly, in lambda cold dark matter, you'd have small galaxies at high redshifts, very faint 21 centimeter signals. And Govind, who was far ahead of his time, at whatever time he was, proposed to build an even bigger radio telescope than the GMRT, which later became immortalized as a square kilometer array. And this was in 1991, even before the COBE results came out, because he realized that the dark matter simulations were already a problem for hot dark matter. And so he said, you have to build a bigger telescope. And two people, Peter Wilkinson and Govind, proposed this in the same IU symposium in 1991. And the square kilometer array is now being built as we speak. So that was the situation in the 90s. Hot dark matter was dead. We were back to, or we had kind of turned down, come to lambda cold dark matter. And the main reason for building the GMRT had gone. So what was the GMRT, or what is the GMRT? So the GMRT is a radio interferometer. It consists of 30 antennas with a diameter of 45 meters. So this shows you about a dozen of the GMRT antennas with the sun setting behind them. And the antennas are in a Y-shaped array with about 14 antennas in the central square in a 1 kilometer region and 16 in 3 arms of the Y. And I've always thought that 45 meters is not a number I can really get my head around. So the best way of showing how big these dishes are is the image over here, which shows the one GMRT dish and a bunch of summer students. And these are common or garden summer students, which means the average height is about typical. This is a big dish. It's a big, big, big dish. And there are 30 of these. And what this means is that the sensitivity of the GMRT is spectacular. The other thing was that Govind had, again, intelligently not put all his eggs in one basket. So although detecting 21 centimeter was the main science goal, he decided to equip the GMRT with multiple frequency bands to allow a range of science. And that meant that the GMRT was a very versatile instrument. And so the fact that hot dark matter had died didn't matter all that much. It was still a great telescope to do all kinds of other astronomy. So the GMRT opened about two decades ago. The first paper came out in 1999, and it's been doing wonderful stuff ever since. And as I said, the GMRT had high sensitivity, but unfortunately not high enough to detect 21 centimeter emission from these small high redshift galaxies that you expect in the lambda cold dark matter cosmology. And then things changed again. Again, what happened was, and this is a standard thing in astronomy, new results are driven by new instrumentation. In the 90s, while the GMRT was being built, a bunch of other telescopes were built. The first of these was the Hubble Space Telescope. The next was, which of course is in space. The next was the Keck Telescope, which is 2 10-meter class telescopes in Mauna Kea in Hawaii. The next was a very large telescope on Cerro Paranal in Chile, 8-meter class optical telescopes, 4 of them. And then there were 2 more satellites which went to space, the Herschel telescope, the Spitzer telescope first, and then the Herschel telescope. So there were these wonderful new optical telescopes and infrared telescopes suddenly out there. In addition to that, there were new techniques. The new techniques allowed you to identify star-forming galaxies at high redshifts, which was very hard to do until the late 90s. Suddenly now these new techniques came in and you had a bunch of great telescopes with you. And then optical astronomers devised new strategies which were essentially to observe what are called deep fields, where you take a single region of the sky and point your telescope at it for a lot of time and beat down the noise so you can go really deep on some region of the sky, some contiguous region, and then observe that same region with multiple telescopes. So you get information, detailed information on all the galaxies in that region. And so this gave rise to what we call the deep fields. And this shows a set of deep fields over here overlaid on a cosmological simulation. The biggest of these is the NOAA Deep Wide Field Survey, which is about 10 square degrees in size. Cosmos, one of the most important survey fields, is about 2 square degrees in size. And there are various of these deep fields now. They've gotten even better since in the last 6 years. But the result of all of this is that today we know thousands of galaxies out of redshifts of 6, way more than 10,000 galaxies, and hundreds out of redshifts of 8. And so our understanding of the stellar properties of galaxies has spectacularly improved. And all of that, I'm going to just show you in a single figure, which plots the star formation activity of the universe. This is technically the star formation rate density, we call the star formation activity, as a function of redshift. And the y-axis is on a log scale. So -1 is 10 times higher than -2. And so what you see is that there's a steady rise in star formation activity in the universe from redshifts about 8 to redshifts about 3. There's steady, this beautiful rise going up over here. And then there's this era from about 11 billion years ago. The time is on the top axis to about 8 billion years ago. There is a plateau in the star formation activity and corresponding to about redshifts of 1 to about 3. This era is called the epoch of galaxy assembly. And the reason for this is that half of the stars that we see today were formed 8 to 11 billion years ago in this era. So galaxies basically built up the stellar mass predominantly in this epoch. We don't quite understand why this plateau happens. And that's one of the open questions of galaxy formation today. And then there is this remarkable decline in star formation activity by a factor of about 10 from around 8 billion years ago to today. So star formation in galaxies was about 10 times higher about 8 billion years ago compared to today. So this begs the question, why did star formation activity slow down? What were the galaxies like 8 billion years ago, and how were they different from today's galaxies? And the corollary is, what's happening to the gas? Because that's what is doing the stuff, is causing the star formation. So what's happening to the atomic gas, especially the primary fuel for star formation? And this requires you to measure the H1 mass of star-forming galaxies at this epoch, ideally throughout this era, all the way out to this period, and preferably beyond, but certainly out to redshifts of 3. You like to measure the H1 mass of star-forming galaxies. But the problem is that I just told you that it's very hard to measure the H1 mass. It's very hard to detect 21 centimeter emission at redshifts larger than about 0.2. So what do? Do you just wait until you build a square kilometer array and hope that you can do it 10 years from now or 20 years from now? Obviously not. What you can do is that instead of measuring the H1 mass for an individual galaxy, you can use statistics. So suppose you had an ensemble of galaxies, and suppose somebody gave you the positions and redshifts of those galaxies. And let's suppose in addition, all those galaxies were within the field of view of your telescope. Now, all of those 21 centimeter signals are within your telescope field of view, which means that you can now extract each of those signals from each galaxy, add them together, stack them, take the average over the n galaxies that you have, and essentially get the average H1 mass of these galaxies. This sounds, relatively easy. Of course, there are lots of complications, but at least it seems like a doable problem. And this was realized in about 2000 by Martin Zwan in his PhD thesis, and by Jairam Chengalur at NCRA at around the same time in 2000. This is not as trivial as it sounds. Galaxy positions are quite easy. Just standard, optical imaging will give you galaxy positions, and with 10-meter class telescopes, you can do this quite nicely. Galaxy redshifts are hard because you need optical spectroscopy of lots of galaxies. Again, times were changing in the early 2000s, and so it is starting to become possible to measure spectra of lots of galaxies. It's still challenging even today, but at least it's a doable problem if you throw enough observing time at the problem. So how do you do this actually? What is this notion of a spectral cube? So when you observe with the radio telescope, what you get is a three-dimensional image of the sky. The 3 dimensions consist of the usual 2 dimensions, which are right ascension and declination. Just the 2D thing of the sky that you see. But what you also see, what you also get is an image of the sky as a function of frequency. And the frequency axis is your third dimension in the spectral cube. If you're just interested in the broadband properties of sources, you simply collapse the frequency axis and you get a 2D image of the sky. But if you're doing spectroscopy, you want the frequency axis. And so you make a spectral cube, and that contains your frequency axis as a third dimension. But remember, your frequency axis, because the galaxy at redshifts of Z will send its 21 centimeter signal to a frequency nu, which is 1420.4 divided by 1 plus Z, the frequency axis corresponds to a redshift axis. So for example, I've shown you a spectral cube over here, where frequency increases in this direction, and the redshift increases in the opposite direction. These yellow things over here are galaxies. If you're making a broadband image, you'll just see these galaxies as they are. But suppose you knew the redshift of these galaxies, then you would know in which plane of the cube the 21 centimeter signal would arise. And now you could extract that plane of the cube and say, okay, this galaxy signal is here, this galaxy signal is in this plane, and now I can align these planes together and try to look at the average signal. And that's what you do in stacking. And that's shown over here, where the movie over here shows a number of galaxies in the first slice, and you'd simply take pieces of those regions around the galaxies and stack them up. This is spatial stacking. You can also stack in velocity by basically taking spectra through each galaxy and aligning the spectra. The red lines show the alignment in velocity. And that's what we're doing over here. You simply keep adding the signals from each galaxy by just going to each plane of the cube, each frequency location, identifying the galaxies whose 21 centimeter signals are in that plane, and aligning them in space and velocity, and adding the signals together and averaging, of course. And so what you see over here as you go along, it's gone now to 70 galaxies, and you steadily see a signal building up in the central region of this image, and also a signal building up in the central region of this spectrum. And of course, you might say that you're doing it spatially and you're stacking in space in the middle panels and in frequency or velocity in the right panels. Why not do both? And that's exactly what we do. What we actually do is that we take spectral cubes around each galaxy and we stack both in space and in velocity. And you produce finally a stacked spectral cube. And then you can take a cut through the spectral cube and you get a spectrum like this. Or you can just make an image of the emission in the center of the cube and you get an image like this. And so what you're seeing over here is now there's about 300 galaxies stacked, and you can see this bright emission circle over here, which comes from all of the signals of the galaxies combined together. There's about 350 galaxies stacked together. And you'll see in a short while, 350 galaxies will not get you very far at high redshifts. So this movie is 400 galaxies. And that's a signal that you see. And you see this nice emission line over here. By measuring the luminosity, the flux density in this line, I can get the average H1 mass. And I can do the same thing from the image. What do you need for all of this? What you need is, of course, a high sensitivity radio interferometer. You need an interferometer because you should be able to separate these galaxies spatially on the sky and also have a lot of them in the field of view. And that's what an interferometer gives you. It has each dish has a field of view in the sky. But when you combine the dish and the 30 dishes, like say for the GMRT, you wind up with a resolution on the sky, which is much smaller than the field of view. So you can actually separate all the galaxies while observing them all at the same time. What you also need is lots of galaxies. Of course, the noise over here goes down like 1 upon square root of n when you average. And so the more galaxies you have, the better it is. What you also want is very accurate positions, which is easy, but most important, very accurate redshifts, which is hard. Because you want to align them perfectly. And if your alignment is off, you will wind up smearing the signal. So for example, if your alignment is off by hundreds of kilometers per second, the signal will go away. The signal is about 300 kilometers per second wide typically. And finally, of course, you want redshift such that your line is inside the observing band. So that's the game basically. So we tried this out using what is called the Deep 2 survey, a Keck telescope survey of 15,000 galaxies in a remarkable region, 0.75 to 1.5, in 7 regions of the sky. And this was wonderful because it covers this very interesting redshift range, 0.7 to 1.5, which includes the end of the epoch galaxy assembly and also some of the decline. So we tried this about 5 or 6 years ago. The problem was that with the old GMRT, with 33 megahertz bandwidth, we could cover only a few galaxies in one setting. So we tried this on 4 of the deep 2 fields. 5 are shown over here. We did 4 of these pointings, and we stacked the signals from around 850 galaxies. We got an upper limit to stack signal, and we got an upper limit to the H1 mass. Not very, interesting, but not very interesting. And then things changed about 3 years ago. And the big change was the upgrade of the GMRT. So the GMRT had these narrowband receivers. I've listed 4 over here. There's one more at 150 megahertz. And it had a narrowband correlator, which should cover only 33 megahertz at one time. And remember, redshifts correspond to frequency. So the wider the frequency range, the more the redshifts that you covered. So 33 megahertz covered a very small redshift range. So we had used the 570 to 660 megahertz band and this tiny bandwidth. The upgraded GMRT had these wonderful wideband, or has these wonderful wideband receivers, which cover from 125 to 1450 with almost seamless coverage. There are small holes at regions which have lots of human-made interference. But at least as important, we have a wideband correlator, which gives you a bandwidth of 400 megahertz. So you can cover 400 megahertz in one shot. So the combination of the wideband receivers, especially the 550 to 850 megahertz, and the 400 megahertz correlator, means that we can cover all the galaxies from the Deep 2 survey at redshifts of 0.7 to 1.5 in one observation. And that is just fantastic. It just means you can nail this problem. It's like it's been designed for this problem, so to speak. And so that's what we've been doing. So the plot over here shows the sensitivity of the upgraded GMRT as a function of frequency. And the first takeaway, forget about the scale over here. The takeaway message is that the bands of the GMRT, the 3 bands, basically have approximately the same sensitivity, which is quite remarkable, actually. So let's look at what this buys for you. What have we been doing? The first thing we've been doing is a 350-hour, a huge band 5 survey of a field called the Groth strip, and that covers this redshift range on this plot. The next thing is a 100-hour first, and then a 420-hour band 4 survey of the 7 deep 2 fields. I'm going to talk about that a little bit more at the end of this talk. And that covers this redshift range, 0.74 to 1.45. And that is this really interesting era in the evolution of the universe. And we've just begun the 3rd survey, which is a 400-hour band 3 survey of a single field cosmos, covering this redshift, this frequency band, and this redshift range, bang in the middle of the epoch, or at the start of the epoch galaxy assembly. And so the idea is that with these 3 surveys, we will get a good view of H1 in the universe all the way out to redshifts of about 3. And the first one was led by Apurva Bera, who just finished his PhD, and these 2 are led by Aditya Chaudhary. And I'm going to cut straight to the chase and show you our results. So here's the results of the UGMRT 100-hour pilot survey. And here we stacked 7,653 galaxies at a redshift of 0.7 to 1.45. And I've just shown you the final result. So that's the image stack that I showed you earlier in the simulation. This is what you see with the real sky. And this is the spectral stack with 21 centimeter luminosity over here, showing this beautiful 21 centimeter signal. And the dashed curve over here shows the 1 sigma RMS noise. And you can see it's way above the noise. It's about a 4.5 sigma result. So this is the first measurement of the atomic gas mass in star-forming galaxies, or any galaxy redshift of 1. And the first thing which we got from this was that the atomic hydrogen mass is larger than the stellar mass. And that is remarkable because in the local universe, let's say in the Milky Way, the atomic gas mass is about 10 times smaller than the stellar mass. So clearly there was much, much, much more gas in galaxies early on in the universe. But the other thing that we got from this was that if you combine the atomic gas mass with the star formation rate, which we could also measure from the radio images, the continuum images, we found that the atomic gas mass could fuel star formation for only about 1 to 2 billion years, which is really short. In the local universe, the atomic gas mass can fuel star formation for more like 10 billion years, 8 to 10 billion years. So what happens is that at high redshifts, although there's much more gas, the star formation rate is much higher in these galaxies. And so we argued that this was a tentative explanation for the drop in star formation activity at redshifts less than 1. What's happening is that lots of gas, but the gas is being eaten up by star formation, and the gas is not flowing into these galaxies sufficiently fast from the circumgalactic medium. And so that was the hypothesis, and that's what we published last year. So after that, we've been doing much deeper observations. We've gone a factor of 5 deeper, and these are the results of the full 520-hour survey. And we've done 520 hours, observed all 7 deep 2 fields for about 75 hours each, 11,400 galaxies in this redshift range. And the high sensitivity means that we can do all kinds of fun stuff now. We can break up the sample in pieces, and we can actually test for redshift evolution. And so this plot over here shows the same spectra that you saw earlier, but now for two redshift ranges. The orange one is for the high redshift bin in the epoch of galaxy assembly, 1.25 to 1.45 over here. The blue one is for the lower redshift bin, 0.74 to 1.25, which includes the epoch at the end of galaxy, after the end of galaxy assembly. And you can see the 21 centimeter signal is much weaker in the blue curve. And that is captured by this plot, which plots the H1 mass times 10 to the 10 as a function of redshift. And this point is from Apurbo Bera's 350-hour growth strip survey. This is the local universe. And these are the two GMRT points at redshifts of 0.75 to 1.45. And what you can see is that there's a spectacular drop in the gas mass of galaxies below redshifts of 1.2 by a factor of about 3. And this is remarkably steep. In fact, these data are consistent with these data. So things don't change very much below a redshift of 1, but there's this sharp drop over here. Basically, there's much less gas in galaxies at redshifts of 1 to fuel star formation. And this is another way of seeing the same thing, although a more interesting way, I think, which is plotting the H1 consumption time scale. The speed with which gas gets eaten up as a function of stellar mass. And what you see is that, so over here, this is 1 billion years. The 10 to the 9 is 1 billion years. And what you see is that the highest stellar mass galaxies, the ones over here, larger than 10 to the 10 solar masses, have an extremely fast H1 consumption timescale. We said earlier that the average was about 1 to 2 billion years. It turns out for the big stellar mass galaxies, it's much smaller. It's half a gigayear, half a billion years in the most massive galaxies. These galaxies are the ones which dominate the star formation rate at these redshifts. And so basically what this says is that if these galaxies have to maintain their star formation, they must accrete gas on a timescale of half a billion years. You have almost no time to refuel them before they switch off. And we think now that this is now the smoking gun that's telling us that it's these galaxies, their death has basically caused the decline in star formation activity below a redshift of 1. And that's encapsulated in both these figures, the short consumption time over here and the decrease in the average H1 mass. Basically, it's saying there's not enough accretion from the circumgalactic medium to sustain the high star formation rate. So that's the punchline of this. Of course, there's lots of other stuff, but I'm going to stop over here. So to summarize, we like to understand galaxy evolution because galaxy evolution is a fundamental probe of cosmology. And to understand galaxy evolution, you must understand both the stars and the gas. The big question in the field for the last 2 decades has been, why does star formation activity in the universe drop over the last 8 billion years or so? And to do this, to answer this, you really need 21 centimeter emission studies to measure the H1 content of galaxies. And this line is really hard to detect, unfortunately, at high redshifts. So stacking lets you combine the signals of many galaxies and measure the average H1 properties. And that's what we've been focusing on for the last few years. The first study that we did with this basically led to the first detection of 21 centimeter emission at redshifts of 1. And we found that the H1 mass can sustain star formation for only about 1 to 2 billion years. And then the deeper study that we've just completed shows that there's an extremely short H1 consumption timescale in the biggest galaxies, which dominate the star formation rate, just half a billion years. And there's a sharp decrease in the H1 mass at redshifts less than 1.2. And these seem to both indicate that the hypothesis that we had, that insufficient gas accretion from the circumgalactic medium causes the observed decline in star formation activity at redshifts less than 1, is likely to be correct. So where do we go from here? We're now pushing even deeper on this with the GMRT. We're trying to do a detailed characterization of the H1 properties. Lots of stuff you can do with the current data, but we're pushing even deeper at redshifts of 0.7 to 1.5. We're pushing to even higher redshifts of 3 in the cosmos field. And the picture is that you would expect the H1 mass will keep increasing if this thing is correct. But it'll be able to maintain the accretion can now balance the star formation rate. And finally, we'd love to detect individual galaxies at redshifts of 1 with ultra deep GMRT observatory, thousands of hours per field, and in the medium term future with a square kilometer array. So thank you very much.
Thank you, Nissim. I think this was fantastic. You of course you kept it in time, and and this is very, very nice. So questions for Nissim. There are of course some chat questions, but now we have time. So I will ask all the people who have typed in the questions to unmute and do actual physical questioning. So Prerna.
Hi, am I audible?
Yes, we are.
Yeah, thank you for a very wonderful talk. I just wanted to ask what is the cause of outflows in galaxies?
So outflows happen because there's well, there's two reasons. That's actually a good question. There are two reasons. In terms of normal galaxies, the main cause is supernova explosions. So when you have a star or a number of stars together which go boom, they basically throw a lot of kinetic energy in the interstellar medium, and that can push gas outside the galaxy. So that's one big cause of outflows. The other big cause is if you have an active galactic nucleus, a supermassive black hole which is accreting, that can actually throw gas out of galaxies as well. But for the normal galaxies that I've been talking about here, it's mainly supernova explosions.
Okay, thank you.
Thank you, Prerna. Raghava Krishna.
Am I audible?
Yes. Yes.
Thank you, sir, for this wonderful and insightful talk. I had two questions. The first is, does the dark matter halo act as the maximum possible boundary of the circumgalactic medium beyond which the gases can't or won't diffuse and stay contained within the halo? So that they get recycled.
Couldn't quite hear you.
Does the dark matter halo act as the maximum possible boundary of the circumgalactic medium beyond which the gases won't or can't diffuse so that they stay contained within the halo and fall back for the recycling process?
Okay, that's an interesting question. I mean, it's not a trivial question to answer. So in reality, the circumgalactic medium is not distinct from the universe. There is the intergalactic medium beyond that. So the circumgalactic medium is kind of the region where the dark matter halo, which is influenced heavily by the galaxy itself, by the processes in the galaxy. But gas is also flowing into the circumgalactic medium from the intergalactic medium, even larger scales. So there is infall happening into the CGM from even larger scales, and then there is infall happening from the CGM onto the galaxy. And the dark matter halo is on scales of about the circumgalactic medium. But for example, suppose you do the same spectroscopy I was mentioning earlier. You can do spectroscopy of quasars, which are now beyond the circumgalactic medium of galaxies, and that's been done. And you can check, so you can actually see kind of a dividing line where the densities become higher in the approximate region of circumgalactic medium, and then beyond some threshold, you will find that the densities of gas become much lower, or the column densities become much lower. So there is gas out there, but that is the medium in between galaxies, which is much more tenuous. But that gas also tends to fall into the subgalactic medium on much longer time scales.
Oh, thank you, sir. My second question is, from your results, does it mean that the stars which formed around ships lesser than one are different from the earlier generations of stars in their conception properties?
Sorry, the stars that formed at redshifts of less than one are not different from the earlier generations of stars? Is that the question?
Yes.
Okay. So so stars at redshifts less than one are very similar to stars at redshifts more than one. In fact, the stars that we see today, as I was saying, half of them are formed at redshifts between 1 and 3. The other half are at redshifts less than 1. There are a few formed at redshifts larger than 3, but very few. And those stars are all what are called, or typically what are called population 1 stars. They are stars formed once galaxies have reached some level of metallicity. Then there are what are called population 2 stars, which are formed when galaxies have much lower metallicity. There are a few population 2 stars in very low metallicity galaxies in the universe today. And then there are population 3 stars, which are formed very, very early on at redshifts of 15 to 20, 10 to 20, let's say. And those stars we would like to observe, we would like to directly observe, and they will be observed when the James Webb Space Telescope, the JWST, comes online in about, I guess, in about 6 months from now. So, but the population 3 stars are the ones which are formed very early in the universe, and they die very quickly. Population 2 stars are in low metallicity, very low metallicity regions. The bulk of the stars today that we see are population 1 stars, and there's no fundamental difference between stars that were formed, let's say, at redshifts of 0.7 and redshifts of 1.5.
Thank you. 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 Than Oh, is that okay?
Okay, sir. Thank you. Thank
Yeah.
you, sir.
Thank you.
And can you suggest some books for learning this
Okay, so
spectroscopy?
the easiest thing would be to just send me a mail, and I'll send you a mail with information. That's trivial. My email address is easily available.
Okay, sir.
Yeah.
Okay. Okay, Raghav Krishna, thank you very much for joining. I move on to so Vivek. I'll come to your question. Can you just wait for a second? Alok,
Sure.
Alok had a question previously. Alok, could you unmute yourself and ask 2 of these questions?
Yeah. A very interesting work and very beautiful presentation, Nissim. Congratulations.
Well, thank you.
I have 2 questions. One is kind of technical, and another is little bit more than that. What is the typical resolution in frequency around the H1 signal that you can achieve after stacking this? Let's say you go up to 0.7 to 1.4, and then also to the higher range. So typical, from your velocity plot that I can see, is it about 50 or 100 kilometers per second?
Yeah, that's a good question. So the resolution that we have is linked to our sensitivity. So these points have been smoothed. So our raw resolution is something like 30 kilometers per second, 25 to 30. And these points are each at 90 kilometers per second.
Okay, so the raw resolution is better than after you massage the data?
Yes, so we do all the analysis on the finest resolution data, especially because the RFI can be the interference can be removed much better at high resolution.
Okay.
So, and then after that, we basically look for the signals. So we look for the signals at all resolutions, at the finest resolution, and then we smooth and then we maximize our signal to noise ratio at some resolution. Okay. But I could show you a plot of exactly the signal at 30 kilometers per second.
No, I mean, I'm just asking whether you can, begin to see finer structures in the spectrum itself in this process.
Yes, in fact, we do. One of the things that I did not show you is a plot where if you take the galaxies which have narrow emission lines and broad emission lines, and if you carry out the same stacking, but now for the subsets which have broad and narrow emission lines, it turns out you have to do that at much finer resolution at 30 kilometers per second. Right. And you find that the galaxies which seem to be face on which have narrow emission lines, which seem to be face on, they tend to have a much narrower 21 centimeter width as well. And so you need to be at about 30 kilometers per second. In principle, if I wanted to, I could get to 15 kilometers per second so the GMRT can give us 16,000 channels. I've chosen to use 8,000 channels over here just because the data volumes are huge. This is about 8 TB of data.
Okay.
Yeah, so it's a struggle to actually analyze the data. So it would double if we went to 16K. But we have used 16,000 channels for the band 3 observations because the RFI is much worse over there.
Okay. Now, quickly, the second question. Yeah. What is the reason, why are the H1 consumption times so small at large redshifts? What is the physical cause? Is it
the physical cause? It's just the highest star formation rate.
Dark matter is distributed at
no, so it's just the highest star formation rate. It's that, so what's happening is that, I think, if you go to even higher redshifts, there's enough, the accretion times are very short. And so basically, you're eating up the H1 very quickly via star formation, but you're also accreting gas very quickly on timescales of 500 million years. So there's no problem. That's what I predict we will see as you go to redshifts of 3. And that's more or less what you're seeing over here, that you have this very high gas mass, and you also have a high star formation rate, and things are fine. But the problem is that as you go to lower redshifts and as you go to high stellar masses, the nature of the accretion changes. So there are 2 possibilities, and there's something which we really want to test. The one possibility is that when you transition to high stellar masses, the nature of the accretion goes from what is called the cold mode of accretion to what is called the hot mode. And that is linked to the mass of the dark matter halo. When you cross about 10 to the 11 solar masses, so at low stellar masses and halo masses, gas flows along filaments, and it kind of falls into the disk along these filaments, and it kind of settles in very quickly. And that's called the cold mode, and it's a very fast way of accreting gas. When you go to bigger halo masses, what happens is that the gas actually falls in more or less spherically, and then it gets heated up to the virial temperature of the halo. Now you have a problem because you need to cool this gas. The virial temperature is about 10 to the 5, 10 to the 6 Kelvin. You need to cool this gas to make it fall onto the disk. And the cooling time for this gas is very large. And so if you move into the hot mode of accretion, you will wind up taking a lot of time for the gas to accrete onto the halo. In the cold mode, you can do it fast. So one hypothesis is that there's a transition that happens in the highest stellar mass galaxies from cold mode to hot mode at about redshift of 1. This is entirely plausible. It's a possible hypothesis. It matches simulation work, although they can't tell us the stuff in detail, but broadly, in terms of physics, it matches. The other possibility...
How can you actually test this out experimentally?
Yeah, so that's what we're actually talking a lot about now. So one way you could test it out is that, so this makes a very clear prediction that the highest stellar mass galaxies should have this dramatic change. You should not see this dramatic change in galaxies, for example, lower than about 10 to the 10. You will see a fairly clear transition, and that transition will keep happening. So for example, when you come to about redshifts of 0.7, you will see that transition. So now the objects which were 10 to the 9.5 solar masses will now start shifting into this hot mode phase. So you will see the same kind of transition happening as you go to higher redshifts with higher stellar mass galaxies. So now if I go to redshifts of 2.5, I should see the same pattern, but I should see it at even higher stellar masses.
Okay.
And so that's what we'd love to check. It's not trivial, but at least we think that this is what we should see. Simulations are not good enough but this is the picture that you get from simulations with a lot of fudge factors. The other possibility, which I can't rule out as yet, which is, I would say, equally plausible, is that outflows are important. The biggest galaxies drive the most powerful outflows. And so now, if outflows are important, maybe the outflows cause sufficient H1, sufficient gas to be removed from galaxies, and that causes quenching of star formation. If that is the case, then I should be able to see this by looking at face-on galaxies and looking for face-on galaxies which have a large outflowing velocity. Those galaxies should preferentially have should eat up their H1 faster. Again, I need much more observing time, but you can see that there is a way to separate these two models.
Okay, and the high frequency resolution will be important for this testing out the latter half.
Sure, yeah. So my feeling is that 30 kilometers per second is fine. Face-on galaxies would have a width of about 50 or 50, 60 kilometers per second. So if you get 2 bins across that should be okay. But okay. I would definitely not want to go below, you want to go worse than 30 kilometers per second. And I would probably like to be about 15 kilometers per second, just to be paranoid.
Okay, great. Thank you.
Okay, I think Vivek has been waiting. Vivek, please.
Yes. Okay, can you hear me?
Yes.
Okay, I have a couple of short questions. One is, are there galaxies where the velocity profile is a function of distance from the center decreases, or at least is not of the same shape? Because I read somewhere that there are a few of these, and what is the understanding of that?
Yeah.
And the other question is, can we say anything about the nature of cold dark matter? Because that is the most plausible theory as of now, as you said.
Yeah. So let's get to the first question. The first one is, yes, there are some galaxies where the profile, where the rotation curve drops, and what that's saying is that the halo is relatively compact. In the context of dark matter models, the halo could be relatively tight, and you're looking at H1, which is the disk is off the order of the scale of the halo, or maybe slightly smaller than the scale of the halo. So you're not picking up that much of mass from the outside part of the halo. So if the halo is so big and the disk is quite extended, what could happen is that the amount of mass that you have in the central regions, even of the halo, is much larger than that in the outskirts. So therefore, you will actually see an approximate 1 upon r square kind of behavior. It usually is not as steep as 1 upon r square, but it could fall. So it does happen. It's not observed for too many galaxies, just because you need to have a disk which is big enough. But it is observed, for example, for these really big dwarf galaxies, where the H1 disk can be really large, or for these giant low surface brightness galaxies, Malin-1-like systems. So it does happen, but it's for a small number of galaxies that such a thing has been observed.
Okay.
So that's one. The second thing is cold dark matter. Cold dark matter is hard. We don't have, there are a lot of possible candidates for cold dark matter. I mean, the classic one from the 80s was supersymmetric particles of the supersymmetric partners of various standard particles would be a plausible cold dark matter candidate. Supersymmetry has not been, there's no evidence found for supersymmetry so far. Axions are an example of a cold dark matter particle, but we don't have any evidence for cold dark matter particles in the lab. So we would love to see something in a particle physics experiment which actually identifies something, at the levels of hundreds of giga-electron or GeV, let's say. That would be a nice cold dark matter particle.
Yeah, but if you said axions, then they would be probably extremely light, and therefore they would be relativistic.
No, so axions are believed to be at least certainly not relativistic particles. They are sufficiently massive to be non-relativistic.
So, of what order of mass do you expect them?
I don't remember off the top of my head, but they're certainly not relativistic. I don't remember the current constraints on axions right now. Then I can get back to you on this if you like.
Yeah. Okay. Thank you.
Okay.
It was a very nice talk. I mean,
thank you.
Very comprehensive and very nice. Thank you.
And all time as well. Fantastically delivered. Okay, Shujay Mate.
Yeah, nice talk, Nissim.
Thank you.
I have a very general question. So when you're comparing the hot dark matter and cold dark matter theories, you said that hot dark matter couldn't explain galaxies beyond redshift 3. And cold dark matter can. So can you just comment why exactly? Like, what was the problem there?
Sorry. Okay. I see what you mean. You mean this issue, right?
Yeah.
That you can't form structures. Yeah. So that's because when the way you do this is that the cosmic microwave background anisotropies give the amplitude of the inhomogeneities in the universe at a redshift of 380 at a redshift of about 1100. Now what you do is that this gives you the initial conditions to form structures. So now what happens is that you basically evolve these, you put this amplitude into your hot dark matter model and into your cold dark matter model. And you ask the question, when do you form galaxies like today's galaxies?
Okay.
And the answer is that you form galaxies, the amplitude is too low in hot dark matter because you form these gigantic galaxies at some point, but even those galaxies form much later.
Okay.
And you never break up those galaxies in time to form normal galaxies by redshifts of 3. So you wind up forming big galaxies very late in the universe. Another way of saying it is that you need bigger structures in hot dark matter. And the reason for that actually is interesting. In fact, it comes back to the reason to why do you expect these supermassive galaxies? So basically in hot dark matter, the particle, the dark matter particle is relativistic, which means that it actually moves fairly fast on the timescale in which the particle collapses in the gravitational field. And the effect of this relativistic motion or this motion is that you smooth out inhomogeneities on some scale. So in hot dark matter, inhomogeneities, structures, if you like, in the very early universe are smoothed out on the scale on which dark matter particle can travel before the structure collapses. And that's the reason that you produce only supermassive galaxies, because on smaller scales, which produces smaller galaxies, you basically wind up, that inhomogeneity gets smoothed out. In cold dark matter, the particle moves a much shorter distance, so you produce smaller structures. Now the time scale on which that structure can collapse is much larger. So you wind up producing later structures in hot dark matter.
Okay, so you need more time to get to the...
basically just need more time, So for a given amplitude, the hot dark matter will produce later structures than the cold dark matter will.
Okay, got it. Thanks.
Okay. Well, thank you, Shujay. So if there are no more questions,
can
are
I
there any?
One quick one?
Yes, please.
Nissim, you are a proponent of extension, or I don't know what you call a more advanced form of the GMRT.
Yes.
New advanced form of GMRT, when it is funded and when it is built, will it answer any of these questions that you have still?
Yes, absolutely. So the reasons for expanding the GMRT are, in fact, this is probably the major science driver for it. So there are two things to do. One is to expand the number of antennas, which increases the raw sensitivity, and that would be great. But there's a deeper thing that you can do. You can actually put what are called focal plane arrays. So right now we have what are called, we have basically single pixel receivers on every antenna. And that lets you cover a very small region of the sky in one pointing. So when you observe, you only cover about 45 arc minutes, let's say, less than a square degree, half a square degree, at about 600 megahertz. Now, what we could do is that we could actually build a focal plane array, and that is like having 30 or 40 receivers over here. And that lets you cover about 30 times larger sky area in one shot. So focal plane array technology is very recent. It's come up in the last 10 years or so. But if we could do this, we could carry out much larger, wider field surveys, and that would allow us to actually detect individual galaxies. Right now, the problem is that our sky area is so small that the probability of having a high mass galaxy in that region is quite small. But if you had a bigger, field of view with a focal plane array, and of course, if you had, like, say, a factor of 2 or 3 increase in individual sensitivity, your chances of detecting individual galaxies redshifts of 1 and directly testing these models on individual galaxies would become possible. So right now we are doing this averaging across galaxies, right? And that makes it harder to pinpoint a galaxy and say, okay, look, I'll observe this kind of a galaxy, which has this stellar mass and it's got this velocity profile. I would love to do that. And if you could upgrade the GMRT and build FPAs, you would be able to do this.
And how unique would this facility be?
It would be absolutely unique. So right now the current telescopes in the world, you have similar facility, you have similar focal plane arrays on the Australian SKA Pathfinder, which is a very small telescope. The collecting area is nowhere near comparable with the GMRT. And the primary science goal there is to look at low redshift H1 out, emission out to redshifts of 0.2, 0.3. The sensitivity is nowhere near enough to get to the epoch galaxy assembly. The second telescope is a Meerkat array in South Africa, which has single pixel fields, but which has very small dishes, lots of very small dishes. The collecting area is less than that of the GMRT, but the system temperature is better than the GMRT. So you wind up with a sensitivity which is less than that of the GMRT, but they're going to do very deep observations, thousands and thousands of hours of observation, and they're hoping to detect at least a few of these galaxies at redshifts of 1. But their sensitivity is still not up there with the GMRT. The time when this basically is a square kilometer array project. And so when the square kilometer array is built, square kilometer array phase 1 is built, then that will become comparable with the GMRT. So if you put, for example, 3 times the number of antennas, that will become comparable with the GMRT. But the square kilometer array phase 1, square kilometer array mid, will not have focal plane arrays. And so again, the GMRT will win because the field of view.
Okay, and next generation VLA has no such projects?
No. So the NG-VLA is designed to go to very high frequencies. So the NG-VLA originally was supposed to be 10 gigahertz to 100 gigahertz. And now they are talking about coming down to 1.4 gigahertz, but that's the lowest frequency. In fact, even the JVLA, the current avatar of the VLA, it stops its high sensitivity part at 1 gigahertz. It's 1 to 50 gigahertz.
Yeah. Okay. All right. Thanks.
Thank you, Alok. Thank you for constantly showing up in colloquia and really making our discussions pretty richer. Okay, Nissim, thank you very much for doing this for us. Unfortunately, we couldn't have you here. That is one of our regrets. But it was a great celebration of your paper. And I congratulate you for your wonderful work and your collaborators for this. It would have been, if it was a physical colloquium, we would have taken you for lunch and tea. Unfortunately, that's what was missing. But we have recorded this in YouTube. I'm going to share it with you through an email. And thank you once again. Thank you everyone for joining in. I know you are checking out right now, but just for the continuity's sake, next week we have Dana Friedman from MIT, who is going to talk about quantum computing using inorganic metal complexes. So hope that most of you can join here. And I would like to thank Mistry and the staff there for constantly ensuring that the lecture room is broadcasting these colloquia and people can come and sit and listen to them. Thank you all for again joining in. So I'll close the YouTube streaming now. And I see Amol has switched on his video, so I guess some comments. Yeah, okay, yeah. So once again, thank you.
Thank you.